So, good. We have a problem of solve problem for which is more losses run. We found very well about management issues. So, good. All right, so we are very happy to have Vinayak visiting us from UT Austin. He's a fourth year at this point. PhD student there, working with Zuckerman, and he's been doing so fantastic work on coding theory, randomness, complexity theory. This is going to tell us about linear hashing, but linear hashing is optimal. Go ahead.
Okay, thank you, Sepper, for the very nice introduction. Yeah, so I'll be discussing some joint work with my academic sibling, Michael Jaber, and my advisor, David Zuckerman. So let's start off with a, okay, I'll just use this. So, okay, maybe I have to click this once here. Yeah. So let's start off with a very classical scenario. I want to toss n balls uniformly and randomly into n. And so, oh, okay, like this. And one thing we like to look at in the scenario is how many balls are in the heavens, as follows. And so it's a classical result in number theory, or not number, in probability that on average, the heaviest bin will have only log n over log n. If you just throw it very randomly arbitrary. Great. And so this sort of property is very useful in theoretical computer science, especially in the design of randomized algorithms and hash. So let me sort of set the scene for what hash is. So usually in hashing, we sort of want to map a very large universe into like a small table, say n to the 100 elements to n elements. And let's say we perform such a map via some randomly picked function. And now let's pick a set of n balls from our universe. Okay, so some subset of size n from U. So pictorially, we have this large universe, and then some subset, some blob of size n is living inside of it. We can think of the hash function as sort of partitioning our universe into n bins, which will be by its preimage. Right? So, for example, the first bin will be all the elements that map to 1, so on and so forth. So what this does is it randomly partitions our universe into n different buckets. So what we want to do here is we want to minimize how many collisions we see in the hash function. And the number of collisions exactly corresponds to the load of a bin, which is what we're talking about. So I'll define the load of the white bin to be the number of balls that map to 1. And then we want to minimize the load of any bin. And so we can define the max load to be the maximum load over all of our. So in this picture, the red part has the most of S, and so that's sort of the maximal bin. And we want to minimize the point so that we want S to be spread over all of our theory. So one thing I want to note is that we need randomness here. If H was some fixed deterministic function, I can always adversarially pick my set of balls so that the max load is n. And this is by just an averaging argument. If I split n to the 100 elements into n groups, one group must have n to the 99 elements, and then I can just fit all n balls into that. So we can't hope to do anything better than n, which is deterministic. But from the first slide, right, we're able to show that if H was fully random, the average max load will be log n over log, right? So obviously not for, it can't be true for every function because of this, the last slide, but on average over a random function, the largest bin will have most log n. So great. Really, what more is there to do? We know random is great. The issue is from a computational standpoint. So picking a random function is very expensive in two ways, time and space, right? So first, there's so many functions from u elements to n elements, particular n to the u. And so it'll take u log n bits to specify. And furthermore, even if you could, it's very hard to compute. You'll have to sort of, without like you'd have to more or less brute force the function. So this leads us to ask, what is the simplest hash family that'll get us this login over log n max load? Then we could maybe hope to implement it. So this question, as stated, is kind of vague. And so there's actually sort of two interpretations of this question. One is to sort of think of it like a video game where I have these two quantities, time and space, and I want to like minimize this as much as I can. And I want to design my hash functions using any tricks necessary such that this will happen. So with this approach, we have really good progress. So there's works in 2013 and 2014 that were able to give a construction of hash functions that use only log n times log n space and can be evaluated in log n squared time. So this is in the word RAM model where a word is like a log n bits. And so one issue with this approach is that these functions, right, because you're allowing any tricks necessary, they're going to be like tricky to implement. If you sort of run them on a computer, the number of operations you'll need to use basically the runtime of it might be tricky just because you're not using just elementary bit operations. And so another point of view would be sort of to account for this weakness is to first look at simple constructions and then try to analyze those, like fix the construction and then now analyze to the best of our ability what the max is here. And then maybe try to prove it's log n over log n or show, no, you have to look at this. So that's the approach that we will try to do here. And so even here, there's maybe one interesting result was in 2012, where Petrascu and Dora showed that there's a simple hash function that's called like simple tabulation hashing. And so this will actually get you optimal max load as well as other hashing guarantees you would want. So this actually can be evaluated in order one time, but one issue is that tabulation hashing requires sort of storing the hash tables that map like a large number of elements to a large number of elements. And so you need a lot of sort of like polynomial space. So that's kind of not so ideal. So a function that we will sort of look at is something that's arguably simpler than even tabulation hashing. And it's going to be linear maps or random matrices. So these hash functions sort of maybe date back to 1969 by the thesis of Zobrist, who I think was trying to like look at how to design a chess engine more or less. And then it showed up more formally in the first paper on universal hashing. So this was sort of set as an example of what a universal hash function. So a universal hash function is just saying the probability that two different elements collide is that of a random function. All right, so okay, what do I exactly mean by a random matrix over F2? Well, remember, we're mapping U elements to N elements. Let's say I add some algebraic structure to these two sets. In particular, I think of these U elements as a log U dimensional subspace over F2, and then the N element as a log N dimensional subspace. So lowercase u will equal log of U. And then for the rest of this top L will denote the log of these two of it. So we have these two vector subspaces. And so now hash function is just going to be a random linear map of vector subspace between these two vector subspaces. That's it. Okay, so one way of thinking about this is via, yeah, a random matrix. So you can think of it as our hash function will just store U column vector. And then for each element in our universe, we map it to our bin space F2 to the L via matrix multiplication. And so all the hash function has to do is sort of look at X, find out which indices it's one on, and then bitwise XOR all vectors corresponding to those. So you can sort of, just from this interpretation, you can see that the space complexity, if we take U to be, if we take big U to be n to the 100, it'll be about log squared. So it'll be like a log n by 100 log matrix, and then you'll require log n operations. So the log n is a bit worse than the constant operations in the previous example, but I guess in terms of space complexity, and I guess implementation, it's a much simpler function. So maybe one other interpretation I kind of want to have you guys think about is back to the pictorial one. Now, so first, if I have a linear map, all of its pre-images, notes, are just shifts of some subspace, in particular the kernel. So now, instead of a weird looking partition, I'll actually now have some structured partition. In other words, I can think of a linear map as first picking a random subspace, tiling my universe with this subspace, and then asking, does S spread well among this partition? So that's sort of the hash. So this is kind of what I really want to like have you guys think. Okay, I have some subset. Is it true if I pick a random subspace, no shift of the subspace will heavily intersect? Great. So now, okay, what do we know? What do we know about the max load of this hash family? So first, let me get the lower bound out of the way. We have a lower bound in a very strong conceptual sense that no matter what family, no matter what hash family you give me, no matter how many bits it takes to describe, no matter what they are, I can always give you a set of balls such that the average max load will be at least order log n over log. So you can't do better than random. So now in terms of upper bounds, I guess we should start with the work that introduced universal hash functions. So they showed that any universal hash function will have max load root n. And so, of course, a linear map is a universal hash function, and so it enjoys this bound as well. So a year later, along with Markowski, the authors showed a polynomial improvement over this generic bound. And then 7 years after that, Melhorn and Vishkin were able to show a sub-polynomial max load bound. And this was the state of the art until 1997, when Alon, Dietzfelbinger, Miltersen, Petrank, and Tardos were able to show a very small bound of nearly log. At this point, there's probably one question you're asking, like, this is very close to log n over log n. Is it true that it could be? And oddly enough, this remained the state of the art. There wasn't much progress since then, with the exception, and oh yeah, sorry, I should say like, yeah, this was also a natural question that was asked by the 5 authors as well. And there wasn't much progress until a note in 2018 basically said that, oh, if Alon et al. Had set their parameters better, they could have gotten a log n max load actually. And so maybe you're asking now, okay, can they have set their parameters even better to then get log n over log? And so we tried, and so unfortunately what happens is, even if you replicate their argument for a fully random function, the argument will only deduce a log n max load. So like this argument is like weak in a conceptual sense where like you need either more input or some different argument to even deduce a login over loglogn bound, even for fully random function. So yeah, so this was the question. Is the max load, is the true max load log n, or could we get it down to log n over log n? And so we're able to resolve this question. And so we show that the optimal, that linear hash functions indeed do enjoy optimal max load. So the goal for my talk, I won't be able to show expected max load, but I'm hoping to be able to show the full proof of high probability. So I want to show you that if I pick a random hash function, so I'm going to first assume the universe is of size n squared. And then I'm going to show you that with probability 0.99, the max load is order log. And in fact, before I even show you that, I'll just show you that the probability is non-zero. So even this is a new result. Even this was not wrong. So in other words, I want to show you that no matter what set S I pick, there exists one linear hash function such that the max load is log again. Or in other words, for any set S, there exists a subspace of dimension L such that no shift of the subspace has more than log n over log n is such. Great. So what is sort of this new input we need? What is this like technique we need that can sort of get us log n over log n? It's potential functions. So, oh, sorry. Yes. Question.
Would you comment using as well?
Yeah. So so maybe I will say, let's see. So this was sort of looking at the collision probabilities, which you can think of as looking at a second moment. This one looked at, right, maybe the 1/4 is giving it away, looks at a fourth moment. This approach sort of does some sort of like union bound approach over all subspaces in your element. And so you get like 2 to the squared log n. And you can kind of show this approach is tight if S is a subspace. And then so this approach, oh wow. So they sort of like, honestly, I don't know how they came up with this. So basically they show a coupon collector property. Basically, you can think of it as if I have n log n balls and n bins, if I randomly hash them to the bins, every single bin will have at least one ball. So this is equivalent to coupon collector if H is fully random. And so they showed this property, and then they somehow use that to then give bounds on the max load. So it's not true anything with a coupon collector property will then have max load, but they use that fact along with some other tools to then get that. So that was sort of how these arguments. Oh yeah.
So for random functions, it bounds work with polynomial high probability.
Yeah, so that's a good open question. Yeah, so for a random function, you would get this with probably like 1 minus 1 over n. We don't know if this holds. So the best bound to get is something like 0.9. And so that's a great open question. If you could you get 1 minus little of 1?
Well, and I guess even the first one, I'm not sure if it gives one once, if it's just pairwise and dependent. So does any of them give you some bound?
Oh, that's a good question. That's a good question that I should check. Yeah, I'm not sure. Yeah. Like if sorry. I guess our work shows of 1 minus little of 1 bound. So our work will say this probability is at least 1 minus 1 over C. 1 minus order 1. So if C becomes super constant. So I guess I don't know if it's implied by the previous work. So I should. Any other questions about maybe even like the subspace version of linear hash? Okay, then I'll continue. Right, so we use potential functions. So maybe your first approach would be to look at, okay, I have this tuple of n, I have an n tuple of loads, and I want to bound the maximum. Maybe I'll bound the maximum of one of them and then like union bound for all of them. The issue is that there's so many correlations, right? In particular, if I knew where x and y hashes to, that defines where x plus y hashes to. So in general, any balls that are linearly dependent will induce correlation. So this gets very confusing very fast, and like it becomes overwhelming to think at. But what if instead of looking at an n tuple, we just sort of try to look at one real number that measures how imbalanced our allocation is? So, for example, maybe we can look at some soft math of the loads. So look at this quantity. So this quantity is supposed to, it's kind of mimicking the maximum in the sense that if one of the loads was large, right? So we're taking the average of the exponentials of the load. If one of the loads was large, then this quantity would spike because that term itself will contribute a lot. And then if all the loads were small, this quantity will stay tame. And so our hope is that maybe we can just keep track of this information and be able to analyze it. And so that's what we're going to do. So to make things formal, I have some arbitrary set of size n, and I would like to find some linear map such that this is balanced according to a linear map. So let's say I have some hash function with kernel v, and I'm assuming it has dimension L. So yeah, for the rest of this talk, assume H is like a surjective linear map. So it's not like the all zeros map. It's something with with minimal kernel. I'm going to define the potential of H to be, again, the average of the load, average of the exponential of the load, which the loads are just the preimages. And so now, again, I want to tell you guys to think about it in terms of the subspace. So picking a random preimage is equal to picking a random shift of the kernel. And so I can rewrite the potential as picking a random shift in my universe, and then looking at L raised to the intersection of S. Okay. So what do I want to say? I want to say if my hash function had large load greater than optimal, then the potential will spike. And so this is a very easy calculation. So if there existed y star with load greater than 4 log L, this potential can be lower bounded just by the contribution of that, right? It'll be, this is the contribution of the expectation term. And we can unravel all this. L is equal to log n. The load is bounded by 4 log L. And then you do the math, the log L's cancel, you get 2 to the 4L divided by n, and that's going to keep going. So what do we know? We know this. If y is greater, if the load is greater than 4 log L, then the potential is greater than n cubed. Okay? So writing a contrapositive, that means if we can find a hash function, or if we can show most hash functions have potential at most n cubed, we're happy. Optimal max load follows. Does anyone have any questions about? Cool. So now you might ask, okay, but did we really simplify the problem? How on earth are we going to find such a function? Right, even just one function. How can you find one function with small potential? Or how can we find one subspace whose shifts have small potential? And the idea is that we're going to take it one dimension at a time. Okay, so instead of focusing on picking a random subspace all at once, we'll just focus on picking one vector. And then we'll pick the second vector to span it, and then the third vector all the way down. So in other words, we'll start with the trivial vector space. We'll pick a random W1 not in the span. We'll span it to get V1. We'll pick the W2 not in the span, so on and so forth. L times until we get our final subspace, which is the span of the L vectors we pick. And so the hope is, maybe it's easier to think about one random vector versus one random sub. So pictorially, I want you guys to see what it looks like. So S will be the blue square. If I hashed according to shifts of the singleton to the trivial subspace, it's the trivial hash where every single element has its own body, right? And so we have a silly little hash here where the max load's obviously 1. And then let's pick W1, which is sort of this vector here. What's going to happen? V1 is now going to be the disjoint union of this cell and this cell. And so we'll have this rectangle. So now we'll be hashing according to this rectangle instead of just individual square. And it'll look like this. Okay. And then we continue this. Let's say I pick W2 to be this vector. Then V2 will be the disjoint union of these two cells. And then so my hash will look like that. And so at each step, I'm sort of pairing up bins via some vector. X is being paired with X plus W. And then I'm slowly halving the number of bins until I reach N. So you can think of it as I start with U bins, I get to U over 2, so on and so forth, until I get to N bins. So does this picture make sense? Okay, cool. Great. So why are we doing this? The idea is that instead of looking at the potential of the final picture altogether, let's look at the intermediate potential. So for each configuration here, I can easily define the potential to just be the average of the exponentials of the loads, where I pick a random shift of that particular, right? So formally, it's this formula. The only difference is instead of V, it's V sub I. Okay. The hope is now, maybe I can analyze phi sub 1 in terms of phi sub 0 easier than phi sub L in terms of phi sub 0. Just one step at a time. So again, let's recall, our potential is equal to the nth step. And so we want to show that there exists some function whose nth potential is infinite. So how are we going to do this? Well, it relies on the following key law. And it's this. What it says is that at any step I, if I pick the next vector randomly, the average potential will at most square. Okay? So let's say I picked my first I vectors and they're fixed. I now randomize over my next choice. The average potential will only square. Okay. So this lemma's true. Then we can already deduce existence by the method of conditionalization. In particular, by an averaging argument, obviously there must exist some though, I plus 1 that will have potential, that will make the potential most p sub I squared. So let me fix such choices. I first fix W1, then I fix W2 such that p sub 2 is small, so on and so forth. And what do we get? I can chain all these inequalities together, right? That means there exists some subspace of dimension L such that the final potential, p sub L, is at most the square of the previous one, which is the most fourth parallel one before that, yada yada, which is at most the 0th potential squared L time, which is this p sub 0 to that. Great. So let's consolidate all that. We know there exists a subspace such that the potential is at most phi sub 0 to the n. And so now it's a matter of calculating phi sub 0 to the n. We know what phi sub 0 is. It's a very easy hash. In particular, there's n squared bins, and n of them have one ball in it. And so the potential, we can just calculate it as, right, the n over n squared many buckets will contribute an L to the first factor, because it has load 1. And then the remaining buckets will contribute an L to the 0th factor, because it has load 0. And then I can bound this by 1 plus L over n, right? You have one term. So then that means phi sub phi is at most phi sub 0 to the n, which is at most 1 plus L over n to the n. And then we apply our favorite exponential inequality here. And then so we get that this is at most e to the L, which is at most n to the log of 2 e, which you can verify is at most. And so at this point, we've proven the existence of one hash function that gives us optimal max load, assuming the key level. So now you're probably asking, okay, how do you show squaring? Right? So how can we show this key lemma? If we show this key lemma, we now deduce existence. And to do that, let's look at the ith time step in more detail. Again, recall that, okay, so actually let me first define some notation. So I'll define S sub I of x to be this quantity. It's the intersection of S with the shift, the x shift of E sub I. In English, you can think of it as it's the number of balls in the bin containing. Okay. And so recall in this time step, what we're doing is we have these bins. If I pick some W, I then look at its shift and I combine the bin with the bin's shift to get this. All right. So with this definition, first I can write my potential easily, right? This is equal to the expectation over all shifts of L raised to the intersection with that. So this lemma, right, we're trying to argue how phi sub I plus 1 grows with respect to phi sub I. And so we want to relate the two quantities. And so it makes sense to try to relate S sub I plus 1 to S sub I. So as a toy, let's look at some arbitrary point, this diamond. And so can you guys tell me what is S sub I of diamond and what's S sub I plus 1 of diamond? Right, yeah, it's 1 and 2. Exactly. So S sub I, how do we figure this out? We look at the ith time step, and it's the number of balls in the bin containing the diamond. It's fun. And then at S sub I plus 1, I look at the I plus first time step, and it's 2. So how did the second one come up? Well, it's because when I look at the diamond shifted by this vector, it's this bin. And this bin also has one ball. So in the I plus first time step, I will have conglomerated them, and so I summed. So with this information, you can now guess what, in general, how I can relate these two quantities. So if WI plus 1 is not in this band, if it's not in B sub I, we can then see by this logic that S sub I plus 1 of x should just be S sub I of x plus S sub I of x plus W. Yeah.
I'm confused about the definition.
Yes.
Aren't you double counting some of the cell?
Yes, I am. Yes, you're right. In particular, there'll be different x values that'll correspond to the same shift. But that's okay. As long as each shift is counted the same number of times, it will be an honest pattern, right? Yeah, as long as I double count each shift the same number. But that's a good count. Good. So we have a relationship here. So this motivates us to define this following auxiliary quantity, which is just, I rewrote S sub I in terms of its lower constitution. So I'm calling this psi sub I. And what we just showed is that these are equal when W sub I plus 1 is not. Right, we just showed this. We showed something strong. They're point-wise, they're the same, but of course that means they're average. Great. So all we have to do is extend this out, and hopefully these terms can be expressed in terms of phi sub I and then half. Great. So this is just recap. These are the definitions. This is what we just showed. And now, okay, let's expand we have this. We can write out the definition of psi, and we'll get this. Expectation over x over all the elements, and w over the elements non-b of this guy. And then at this point, at least I got stuff. I don't really know how to, like, I think maybe, like, how would we, yeah, how do we simplify this more? In fact, what's annoying is that this average is like, it's not over the whole thing, it's over like the smaller domain. And so I can't even split this. Yeah, so like basically, this is probably the most annoying part, that the average is not symmetric. In particular, if I did in a magic world where the average was symmetric, so now I'm averaging over the whole universe rather than without the span, then I could simplify this. In fact, I'll get my dream, right? So what I do is I get this expression. And so here I'm using the fact that if x and w are random vectors, random, uniform, and independent vectors, so is x and x plus w. Okay. And the reason is more or less because this is like an invertible. And so it's kind of like a chain. So I've replaced x with w, because these are the same distribution. And at this point, I have an expectation of a product of independent variables. So I can write it as a product of the expectation. And look what we have here. These two, right? It's just phi sub I. It's by definition. So we'd literally be done if it wasn't for this. So that's kind of annoying.
I'm saying
Yeah.
boy or job. So what was wi plus one?
W I plus one. Oh, what is it again?
This comes to the I plus one as column of the hash function.
No. So here we're fully right. We're fully in the kernel slash subspace interpretation. I don't know if there's a nice way to look at the columns and relate it to the.
But in the subspace interpretation, this is when you're repeating the I plus one as element of like the basis of the subspace.
Yeah, exactly. So exactly. So like right. So maybe I should have said S of I will depend on the first I vector space. And
But
then
isn't vi a very small part of that?
yeah, so that's one way of finishing. So one way you can finish is say this is contributes a very small probability. So maybe it won't be squared, but it'll be squared times 1 plus epsilon. And this works. This just 100% works. The error is small enough so that when you compose, it just becomes a constant, and it works. So I guess here's an alternate argument that lets me get the square immediately, or it gets the square without the loss. But yeah, that's 100% valid. Great. Yeah, so we have the average over everything. It's phi sub I squared, but we want to know the average without the v. So maybe, what if we could show the average inside the v is greater than phi sub I squared? That would then imply the average outside the v sub I should be less than phi sub I, right? So let's try to show that. So again, recap of all the definitions. Now let's focus on v sub I, right? We want to know what happens when you pick w sub I to be inside v sub I. So what do you guys think will happen if I had some element x? What bucket will x plus w be? Yeah, the same bucket, right? So this is what will happen. And I guess, yeah, as you said, it's simply because if I take x and add w, the shit x plus w plus v sub I will be the same as just x. Just because this is a subspace and then adding it onto the subspace, we keep it. Wait, so what does that tell us? X and x plus w are in the same bit. And so as a corollary of this, the number of balls in the bin containing x plus w must be the same as the number of balls containing x, because it's the same bit. And so I can actually directly then figure out this expression, right? This expression is equal to the expectation of L raised to the sum, but this guy is equal to S of I of X. So it's just this. And then now we use our favorite inequality, Cauchy-Schwarz, or maybe convexity of the square. And so you get this is lower bounded, but this quantity where I take the square outside. Look what's in here. It's just C sub I. And so great, we've shown that the global average is V sub I squared. The average within V sub I is greater than V sub I squared. And therefore, the average without V sub I must be of most V sub I. And so that concludes the proof of the Q lemma. Okay. But it doesn't conclude the proof. It doesn't conclude what I promised, right? So at this point, we've shown that there exists a hash function. But we still need to show it happens with high probability. So it's been a while, so let's recap the whole argument in just like 3 short lines. We first showed the potential is at most NQ, then the maximum is at most 4L, or log n over log. And then the zero potential was 1 plus L over n. And then we had the key lemma, which showed that expectation conditioned on the first I potentials, the average of the next potential of most squared. If we use method of conditional expectations, this allows us to use there exists a hash function whose final potential is at most the original potential to the 2 out, and that got us the result. So now, if we want to get probability 0.99, we naturally want to ask, well, can we get this found with high probability rather than just with non-zero? Right? So now we have this interesting question where we're given random variables satisfying this conditional expectation rule, and we deduce a tail bound. So to make things easier, we don't really care about the 3. Maybe the 3 is hard to do, matching exactly existence, but we only care about order log n over n. So we can replace the 3 with any constant we want, right? So like if C was a billion right now, maybe not the practitioner, but right. So let's say, can you just get any polynomial tail n to the C for any C? And so this is the question. So maybe at least one very tempting approach is to sort of chain this expectation. Like, oh, maybe if expectation of phi sub 1 is phi sub 0 squared, expectation of phi sub 2 conditioned on phi sub 1 is phi sub 1 squared, maybe that then implies the expectation of phi sub 2 is phi sub 0 to the 4th power. And so then maybe you would be like, okay, the expectation is something like this, and then your cost, right? So the issue is you can't do that. So in particular, I can give you variables phi sub 0, phi sub 1, and phi sub 2 that satisfy this conditional thing, but it'll have infinite. I don't want to get into construction, but it's just simply, it uses the fact that there exist random variables with finite expectation, but infinite variables. So you can play with that to get such a thing. So yeah, this is not true. So in fact, you cannot, the expectation of phi sub L might be large. So does that mean the dream of a tail bound is over? No. So what we show is that even if the expectation is large, it's so skewed that it still enjoys tail bounds. So okay, so let me dissect this. I've abstracted out the potentials and I'm just focusing on the expectation. So I have L random variables, or I have a constant x of 0, which is the initial potential. And then I have a sequence of random variables greater than 1, such that the conditional expectation squared. And then we can show a tail bound of this following. So maybe the tail bound is a little weird to think about, but you can sort of think about plugging in t to be like x sub 0. And that's kind of what we want to show. So let me just go through how we use it, right? Recall phi sub 0 is 1 plus L over n, and phi sub 0 to the 2 to the L is something like n cubed. This guy, I can write it as n cubed to the c over 3, and then plug in the phi sub 0 to the 2 to the L, as follows. And then this, it looks very similar to the lemma we proved. And so I just plug in t equals this guy. Well, maybe square root it, but yeah. So you'll get this quantity. And then now we're using the fact that, so phi sub 0, it's like 1 plus epsilon. And so 1 plus epsilon raised to the n will be something like 1 plus n epsilon. So I'll like literally use that approximation to get this quantity. And then this is just 3 over c. So in general, I can pick c large enough so that this guy will be 0.01. So this is what I meant by, oh, the max load is greater than c log n over log n, the probability point. This is exactly. Great. So if we can show this theorem, then we'll be done by sort of this calculation. We'll have such delta.
So for your
Yeah.
you don't need any bound on absolute value of x size.
It should be at least 1. That's important.
But upper bound they can go to infinity.
They can, yeah. But then, right, it'll turn out that the probability will be very small, so it doesn't matter. But yeah, no assumption on the bound.
Where does that appear that the problem comes to a small?
I guess I was saying, even if the xi's are really huge, the tail bound, I guess, implies that it couldn't have happened with that. So yeah, so let me go over the proof of this claim. Yeah. This one.
What is your key here?
Oh, t here will be phi sub 0. Wait, no, phi sub 0 to the
Just
2c over 3. Sorry. So yeah, I should have not skipped this step. So if you plug in t to be phi sub 0 to the 2c over 3, you will get phi sub 0 to the 2c over 3 times 2 to the L minus 1. And then the 2 and the 2 to the L minus 1 combined to 2 to the L. And then, right. So, oh yeah, this exact. So I plugged in, so this is exactly.
It's kind of saying for you to be fully n times larger than the expected value, that probability happens with some one, like a small
Right, yeah, exactly.
prove a big constant, like around expectation is just polynomial, like
Right. In this like potential domain, but then it translates down to, yeah, I guess, because we're taking exponentials in this domain, not corresponds to just the constant value. Yeah, it's true. Good. So yeah, like an interpretation is we were able to show repeatedly, like phi sub L could be the repeated square quantity, probably greater than 0 by a method of conditional expectation. But what this is saying is, yeah, with the polynomial loss, I can actually boost it to out. Good. Good. So how do we prove this? So actually, I think writing out this statement in that form is kind of like maybe one of the tricky parts, and then it will lend itself nicely to an. The proof will induct on L. Okay, and so for the base case, it'll actually be quite simple. So we want to show this is true. And to show it, we'll just apply Markov's inequality on x of 1 minus 1. Right? Because we know the random variables are at least 1. So we use the full power of Markov's. And so you'll just get this. Okay? It's the most that, and then the expectation of x1 is at the most x of 0 squared. Okay, good. Now, so let's assume for any sequence of L variables given to us, satisfying this statement, we have such a bound. We'll now prove it for arbitrary choice of alpha. That's what. So the way we're going to do this is as follows. We're sort of going to reduce L plus 1 to L by first sampling x of 1. Okay. And then I'll condition on what I see. Once I condition on what I see, I now have a sequence, a suffix sequence of size L that satisfies the theorem statement, where now the seed is x of 1 instead of x of 0. It's the value that we observe. And then we could, conditioned on this x of 1, we can bound it by this quantity, but then now you have to unravel that condition. And so that's what we're trying. So formally, to write this, right, probably x of L plus 1 is at least t to the 2 of L, right? We want to show a bound of this one. I plugged in L plus 1 in the above. I can first condition on x of 1, and then look at the probability x of L plus 1 is at least, so I wrote it like this because I want to use the inductive hypothesis. So I put a t squared raised to the 2 L x 1, conditioned on what x. So by, I guess that like little, I don't know, yeah, some law, you have this. And so by the inductive hypothesis, I have a bound. It's just going to be that above quantity where I plug in x of 0 with x of 1 and t with t squared. And then obviously a trivial bound is 1. So I have this following. Right? Is everyone on board? Good. So at this point, we now want to bound this. And this is a little tricky. Like x1 could be anything, right? It could be unbounded. In fact, all we know about x1 is its expectation. Right? We know the expectation is at most x of 0 squared. What can we even bound if we only need the expectation? Well, by linearity of expectation, we can bound any linear function on x of, right? So, right, if we can bound any such quantity like this by this. So this has us think, what if we can bound this function by some linear function in S? Then I could conclude. Right? What's the best linear upper for this internal function? So to find that, let's so here's a graph of this guy. Okay. So you have a parabola. All right. So this quantity, if you think about, so x1's on the x-axis, y is on the y-axis, and then this guy, it's going to, if x of 1 is greater than t, this quantity becomes greater than 1. And so this 1 will take over. So we have straight line 1. Before it, we'll have this expression take over. And this is the parabola, right? The parabola. And so the question is, oh, and then we also know that x of 1 is greater than, right? So the question is, what's the best line that upper bounds this function? And I think it's a little vague question, because I think there's two possible answers. Could be one of these two lines, right? Both of these lines in this domain sandwiches this function. Can someone tell me which line we should go with and why?
You know, that one's very boring.
Boring. What?
Just bombing.
That's true. Yeah. So exactly, like this wouldn't get. So maybe another way is, yeah. So like this would just get you a 1 down, get you that thing. Also, another way to think about it is, by design, T is supposed to be a tail, which means x1 loves to hang out below T. And so that means we'll have more weight, we'll have more gain if we can bound in the area where x1 loves to hang out. So that's why we want to choose this guy. And so now, do you guys remember? So what's the equation in this line? Do you guys? Okay, I want to let you guys. But yeah, we have 2 points, right? This guy, we know it goes through 1, 0 because that's where this guy intersects the x. So we have, so what's the equation of the line going through t comma 1 and 1 comma 0? Well, it turns out it's x minus 1 over t minus. Right? Okay. Okay, good, yeah, it is. So, and then so that gets you the expectation of x minus 1 over t minus 1, and that gives you the inductive set. And so that proves this theorem. And so now we're done. We've shown with high probability you get and so at this point, let me just state some, like, what are all the results we prove, as well as follow-up question. So of course, right, I said, oh, we showed an expectation, but actually what I showed is not strong enough for expectation. If you have like 1 over c decaying bounds, that's not enough to do expectation, more or less because 1 over x integrated, like the sum 1 over x doesn't converge to a constant. So what we show in the paper actually is that it is in a square manner. So one interesting thing I wanted to mention is that lemma, this lemma is actually typed. So I can give you a sequence that exactly gets you probability x of 0 squared minus 1 over t minus 1 for any x and t. So that might make you lose hope that, oh, we can't get anything better than 1 over c. And so what happens is these potential functions magically possess another property, not just these, but the fact that they jump. So in the sense that the next potential sort of not only does it increase, but it jumps in the sense, but like in the sense that its distance to 1 doubles. And so it turns out if we add that into this statement, you can sort of, it'll be a more technical version of this, but this is the intuition. You're finding lines and figuring out the equation of lines through 2 points, and then you'll get the square. So that was kind of weird to me. Because like, yeah, without that property, you don't have it. So it's kind of interesting. Yeah.
So if we go back real quick. Sorry. So at first, you only have the bound on the expected value of x1 squared, right? And here you're, oh, but they're bigger than,
Yes, yes.
so they're always bigger now. So if the expectation of x1 is less than the expectation of x squared, that's why I have the less than e.
The expectation of, oh, sorry. So I guess
That's okay.
I'm like, oh, wait,
Okay. Yeah, the 11 has statements, that's fine. Is that a typo there?
oh my god. Oh my gosh, no square. There should be a square there. Oh dear.
So this expected value of x I plus 1.
Yes, condition, yes. Oh
Sorry.
my gosh, I'm sorry. That should definitely not, yeah, it should just be x of I plus 1. Condition on x. Oh my god, yeah, sorry.
It's okay.
Yeah, good. Yeah, that, okay. Okay, yeah, sorry about that. Good. Yes. So yeah, we showed this, and this implies expectation. So in a sense, this is sort of the strongest result we can show about Maxwell. And it's a good open, like, we don't know if this is tight. I mean, for all we know, this could be much, like, maybe you could show even like it's a little of 1 in terms of n. So like, we don't know if this is tight. We also show, right, so all of this, everything I said generalizes to not only if the dimension of the universe is 12, but any arbitrarily large. It also generalizes if the number of balls and bins are different. In the sense that for any n and n, I have a quantity that represents the max load with respect to a random function. And then I can show the probability of random linear map has max load greater than c times that quantity is at most 1 over c. The difference is your base, instead of being L, is some other quantity, right? And then when m is even larger, sort of in the coupon collector regime, when m is greater than n log n, we can show 2-sided bounds using potential. We can show every bin has about m over n balls with high probability. And interestingly, to show the lower bound, you'll set the base to be a number less than 1, because then it will detect whether some ball has few has small number. And so 2 open questions. One that's very interesting is for F3, can you prove it? So we know for F3 or for Fp in general, the best we know is something like log n raised to the log base 2. So actually, this is approximate. I think for p equals 3, the best we know is that the log is base 3/2. Yeah, but these techniques for certain technical reasons do not translate over to even. And then another question is, can we? So maybe one, not so like. So one thing is, can we de-randomize this construction in the sense? Can we make do with just a log and seed family of linear hash maps versus all of them, which would require log squared n? So our work actually implies that a random set of size polynomial n will give you optimal. And I think this was not known before. However, it's not open whether you can non-explicit, where you can explicitly get. So I think that's another interest. There's a lot more, but yeah, these were like maybe the. And so yeah, that's all I had. So thank you for this.